So in the last video, we now know how to handle a epoxide only if it's symmetrical and only if we put it in an acid condition. All right, so think about those rules, think about those guidelines as you begin to dissect some of these reactions that they will throw at you for the epoxide category or section in your chapter. So we want to move on. We want to talk about an unsymmetrical epoxide. Now, we said symmetrical epoxides, it doesn't really matter. You break open the ring, you destroy that three-way that's going on, and the incoming nucleophile will add on to either carbon. It doesn't really matter which one it goes. The hydrogen will protonate the O of the epoxide. It breaks open the ring. OH is on there for that reason. And then, depending on what we add, a halogen, well, that halogen goes onto the other carbon. Water, the OH adds onto the other carbon. Alcohol, the O, and then the alkyl group, in our case OCH3, went on to the other carbon. So those don't have to think about. Not rocket science there. Okay. Now let's look at an unsymmetrical epoxide. Let's look at CH3, CH, CH2 with a ring. And we're going to add on to this, I don't know, CH3OH. Let's just change it up a little bit. So there we go. So we know that alcohols have a hydrogen. That hydrogen can protonate, and in addition to that, they could be very good to you, and they're just going to put H plus there, just to let you know that it is acidic conditions. Okay, well, if this is acidic conditions, and we look at this epoxide, the same type of mechanism is going to take place. I'm going to start off by drawing my reagent like I do every single time. We have to start somewhere, so that's a very good place to start right there. And the acid is going to protonate the O, and that creates the OH. And this is what forces the ring to open up. Now we have a question. If we cleave the bond here, that means OH goes on the end. If we cleave the bond here, then that means the OH bond will go in the center. And those are two different products, right? I can draw both of these. Let's draw both of these down here, just so that you can see the difference between the two. So if we erase this bond, boink, there it goes. And that is an OH group because it's been protonated. There's my OH. Well, this other carbon is going to get the OCH3 from the alcohol. Again, think of this as H and then OH piece. All right, so let's do this again, and let's do it the other direction. So here's the epoxide. And this time, let's break the bond to the right. Beep. There you go. And that H from the alcohol kind of goes there. And then think of it as the OCH3 that goes here. These are two different products, folks. So I'm going to get both of these. But which one is the more preferred one? There is a major product and a minor product, and the major product is going to happen in a very large amount. So there is a difference. There's a decision that this oxygen has to go through. So if you were oxygen, what would you do in oxygen shoes? So let's think about this. We're going to protonate the O. When we protonate the O, there's the oxygen of the epoxide, and it's going to go, okay, I'm getting ready to break up with these two cray-cray carbons. And I've got to make sure that I just don't break up the wrong one, because one of them could cause me a little bit more trouble than the other. Well, how do I know that? Take a look at the types of carbons that are there. One maybe has never been in a relationship in his or her life. And when you break up with that carbon, things are going to go crazy. That is the stalking. That's the king, the car, flattening the tires, showing up at your workplace. I mean, you talk about crazy. There you go. The other one maybe has been in a relationship before. And when you break up with this carbon, it's going to be another day. Whatever, there's another fish in the sea. That's how this carbon's going to look at it. This carbon has to, the oxygen has to make the proper choice. Which one is going to be more stable? Because that's the one that the oxygen is going to cleave and say, bye-bye. I was happy, it was good while it lasted, but this is not working for me anymore. Sorry. So this oxygen looks at this carbon, and this carbon is secondary. And this oxygen looks at that carbon, and that carbon is primary. So out of the two choices, folks, oxygen is going to leave behind the one that it feels more comfortable with, and a secondary is more stable, mentally more stable than the primary carbon's going to be. And because of that, it's the bond to the left that's going to be preferred. That's the one that's going to be chopped. Oxygen and carbon's going to end it, and because of that, this is going to be the major product. Did that surprise you at all? I hope that it didn't. I hope that when I talked about secondary, primary, you automatically knew where I was headed with this description. Because this is something that's not revolutionary in any of the lecture material that we've talked about so far, right? It's always about the stability of the carbocation. So if a bond is going to break, then that bond is going to be toward the one that is more stable as far as a carbocation when it's formed. The issue here on the right-hand side, when that bond breaks, it leaves behind a primary, and primary carbocations are not very stable. The molecules do not like to have them around. So this does form very, very small amounts. We get mixtures. We always get mixtures in organic. But here is a major product, and there is a minor product. And that is how we determine this in a acid, ding ding, okay? Let's kind of remember that, an acid mechanism. Base mechanisms are not this way. All right, now, let me change it up. I'll show you how easy this would be. Let's pretend that this was not an alcohol. What if instead of an alcohol, what if this was water? Same decision. Water, think of as HOH. There's your two pieces that you need to add on. All right, well, here's the first hydrogen that was added on from the water. And now what we have is the OH group that's left. So it's the OH group that goes on instead of the OCH3. Okay, there's no difference here. The mechanism happens the same. We make the same decisions. The oxygen is protonated. That protonated oxygen makes the decision to leave behind the more stable carbocation. That more stable carbocation leads to our major product. In this case, it's H, and then on the other carbon, the OH remaining group was added on. That way, that carbon could have 4 bonds. That was the buddy that came and distracted that carbon that was in the relationship with the O in the three-way triangle. Okay, well, if we didn't use water, well, we said we could also use acids, right? And those acids could be HCl or HBr. Same deal, folks. There's no difference. Hydrogen will protonate. That's what we're going to see go on there. And then the other carbon will get the remaining piece. So what's left over once you take the hydrogen away? There's a chlorine left over. So the chlorine is going to go into the other spot. That is all the epoxide reactions do. That's it. The epoxide reaction opens up the ring. OH goes on 1 every single time because the oxygen is there from the ring. So that will always be an OH group. You'll always end up with an alcohol. Now you see why these reactions are tied up in the alcohol reactions. We are making an alcohol here. And then from this alcohol, we can do any of those other alcohol reactions that we want to do. But this is one way that we can form it. And then the other carbon gets the nucleophile that's coming into the picture. Now, those are acids. Let's talk about bases. Bases, look for the negative. This reaction happens a different way because it's a different mechanism. What does that even mean? Well, let's look, right? Let's use the basics of organic to look at this reaction and figure out what goes on. So let's say that we have a unsymmetrical alkene, or epoxide, sorry. So I'm using the same one that I did before. And what if we use OCH3 here? Not an acid. It's just a methoxide. Remember, we got to get methoxide from somewhere. They typically come from salts. So you might see an Na put onto the front of that, or you might see a K put onto the front of that. But this is a salt, an ionic compound that gets dissolved in solution, and these two things react with each other. So what happens here? It's not the same mechanism, is it? You should know that. I shouldn't have to really tell you that at this point. Why is it not the same? Look at this oxygen. This oxygen we said was negative, partially negative due to the electrons. Well, this is negative too. In the acidic conditions, hydrogen was added first, and hydrogen was added because hydrogen was positive. But this oxygen, it looks at this molecule and it goes, ooh, no, I don't want anything over there. I don't want what they have. And then it comes back. And the reason is because they're both negative, and negatives will repel each other. So this is not the mechanism that happens like it happened with acid, and that is why that negative oxygen is not attracted to that negative piece at all. So the mentality here has to change a little bit. What is actually going on for this reaction to take place? Okay, well, think about that love triangle. Here you have an oxygen, and it's seeing two carbons at the same time. We got a big love triangle three-way going on right here. I mean, this is like your husband and wife and then the pool boy. Oh, gosh. Disaster's getting ready to happen. It's just sooner or later something's going to happen. What's going to happen? And we just got to figure it out. You know, does the person run away with the pool boy, or does the person run away with the husband or the wife? That's the decision that this epoxide is going to have to make. Well, that decision is going to be based on the surroundings. That decision is going to be based on this nucleophile. So this nucleophile is looking for a relationship as well. So this nucleophile is going to come in. Maybe one of the most handsome people on the block, or one of the most beautiful people on the block, comes over. Maybe this is the neighbor. Knock, knock, knock. Hey. And they show up. Well, that OCH3 knows that those two carbons are in trouble. That oxygen is pulling away everything that the pool boy has. And then that oxygen's pulling away everything that the husband or wife has. And these two carbons are devoting their time to that oxygen, but they're kind of not getting anything in return. And also keep in mind that the pool boy and that husband or wife also have this bond going on as well. Oh, things just get too complicated here. What does organic chemistry do to people? So this oxygen's going to look and it's going to say, okay, I'm negative. I'm looking for something positive. So out of the pool boy and out of the husband or wife, which one of these is going to be more positive? Which one of these would be easier for me to get to and persuade and take advantage of? Notice what I said, easier to get to. So this means that the nucleophile is going to help satisfy the one that's crazy the most, because it's going to come in, take advantage of that carbon, and that carbon's going to be distracted so that oxygen can break ties with it. So out of these two carbons, we know that this one is secondary and this one is primary. So just like before, that oxygen is going to make sure the cray-cray one kind of is okay and distracted. In the acid mechanism, the oxygen said, okay, I'm going to end it on the secondary because you're a big boy, you're the pool boy. You're the big boy. You can take care of yourself. I'm going to end it. This is not working for me anymore. And we leave a secondary carbon behind, and that's where that group goes. In this case, though, that decision is different because the nucleophile is going to come in from the base and it's going to go, there is the most unstable one. So oxygen, I've got your back. I'm kind of your friend. So because that carbon is the most unstable, I'm going to go to that carbon because it is more unstable. It's easier for me to get to, and I will take care of this cray-cray one for you. That way you can cleave this bond and take those electrons and go off onto that center carbon. So what we see in a base catalyzed reaction, here's CH3, CH, CH2, and there is the epoxide. One version will break the bond here, and the OCH3 group will go on to that end. That frees up this negative oxygen, and now this oxygen's saying, wait a minute, I really liked that two relationship thing that I had going on, and I kind of missed that. I want that again because it's negative. It wants something there. And what it wants there is possibly the easiest thing, a hydrogen. Well, where does that hydrogen come from? We typically use a matching alcohol, just a little bit of it that matches the nucleophile, or we can add maybe acid in that second step. So this is kind of step number 1, and this is step number 2. So we allow the epoxide to open up, and then in the second part, we add on something like water, or we add on something like an alcohol, something that could donate a proton, and sooner or later that oxygen that's negative does get a hydrogen from that source. So that is number 1 product. This is also what we would call the major product. Again, it's major product because that is the side that the oxygen would prefer to cleave on. Now, we do get the other option. I'm just going to go ahead and draw that product because I want you to understand that both of them exist. So the OCH3 could come in and attach to this one instead. And when it does that, that opens up this bond because that carbon doesn't need that 5th bond anymore. And then the hydrogen would go and add on to that O, and the alcohol group would be on the end. So this does happen, but it's a minor product. It is very low in percentage, and we typically just don't even bother writing it. But folks, this is how a base mechanism is different than an acid mechanism. It flips pretty much the side that oxygen will cleave on. So if I want to do a summary, I can. And here's a slide that kind of wraps both of those up. Here's a unsymmetrical epoxide, and the carbon to the left will be the attack under acidic conditions, which means oxygen's protonated first. It knows that this carbon's more stable. That oxygen has to make the first move, and this gets cleaved. So that is the site of attack when a acid condition happens. On the other carbon, though, you're seeing that the opposite goes on. The base attacks first. So when the base attacks first, it knows that this carbon is the more unstable one, so it takes care of that in the very first step. So the nucleophile goes on there, and then the oxygen will cleave on that side instead. So, like I've said before, epoxides, the first decision that you have to make, is it acid, is it base? And then the second decision that you have to make, is it symmetrical or is it unsymmetrical? Because all of these are going to really play a role in the decision that you're going to have to put forward to answer these questions with. All right, let's look at another example. Let's take an epoxide. So there's my CCO. And let's say that I've got 2 hydrogens on here, but we'll do 2 CH3 groups right there. And let's say that I bring in CH3 carbon triple bond C with a negative. Oh, look at this. I mean, we've seen this kind of stuff before, folks. We saw this in the alkyne reactions back in Chemistry 251. That was Orgo 1. Do you remember that? This was a way that we could use the acetylide ion, and we could take the acetylide ion and react it and chain elongate. Well, this is another way of looking at chain elongation. I'm tying all of these loose strings together and making it one big old organic blob for you to worry with. So let's think about mechanism. Is this an acid or is this a base? That's the first question, remember? Okay, well, I hope you're going to tell me base, and it's a base because you see that negative. So you know that this piece is going to come in and say, oxygen, I've got your back. So if you want to cheat with the pool boy and the husband or wife at the same time, I'm here to take one of those off your hands. So oxygen says, thank God. I'm going to break up with the cray-cray one. So you take the cray-cray and leave me alone, and that way I go to the other one, the more stable one. So that base says, okay, fine. So if I look at these two possibilities, at these two choices, where does the nucleophile attach to? Which one is more unstable? So this carbon is only attached to one other. That makes that a primary. This carbon, well, this is a tertiary, isn't it? There's two carbons here and one carbon to the left. So out of the two choices, the cray-cray one here is the one to the left-hand side. So that nucleophile says, okay, I'm going to attach right there, and you can take these electrons and move them on up. So that's kind of the mechanism. I wouldn't ask for the mechanism. I would just say, what is the product? So let's redraw the starting reagent. Again, you know I like to do this every single time. And here is the epoxide group. So what we would see here is that this bond would break, and the carbon that had the negative triple bond to the carbon that has the CH3 group would go to the left-hand one. And then this oxygen has to be satisfied. So in step number 2, we're going to throw in some type of H+. So step number 2, some type of H+ is going to go in. So that way we can create the OH group that should be on to that molecule. So there's the product for that reaction. This reaction was done in a base. That's because it's listed in the reaction as a full-blown negative. That's the dead giveaway. So only after I allow that reaction to take place for a little bit, maybe 30 minutes, maybe an hour, then I'm going to go back and add on step 2. And step 2 is the proton. So only when that first step happens do I add in the proton source. Let's look at another one. Here's CH3, CH, CH2, and then epoxide. And in this case, we're going to add on CH3, NH2. So is this acid or is this base? That's always the first question. So I'm going to look at the CH3, NH2, and I'm looking for a negative, but I don't see a negative, right? I mean, this one's maybe a little confusing. And I don't really see a positive either. So what is this? What type of reaction goes forward? Well, there's something that you need to keep in mind. Anytime I see the NH2 groups are called amines. We've talked about amines because this was all the way back in substitution. And we said that amines were the Miss Americas of the bunch. They were the best nucleophile. Ding, ding. Do you hear that? The best nucleophile of all of the nucleophiles. The best base of all the bases. That's why those really replaced everything that they could in a substitution reaction. So they just assume at this point you know that NH2 is a base. I don't need the negative to come around. It is a base. So because it's a base, this piece as a whole, this piece looks at these two carbons and it says, I'm here to save the day, oxygen, my buddy. So which one do you want me to take? Because that's the very first step. And oxygen's going to say, I need you to take over the crazy one. So this carbon is a secondary. This carbon is a primary. And that nitrogen says, okay, not a problem. So this one is the crazy one. So that's where the NH2CH3 is going to go. When that happens, nitrogen has an extra bond. It's got 4 bonds now. This is going to form a positive nitrogen, and that's okay. That's the weird thing about nitrogen here. That's fine for now. And then when that happens, this bond breaks. There it goes. And then we need a hydrogen source, right? We always need a hydrogen source so that way we can put that hydrogen onto that oxygen to make the alcohol with. So where does that hydrogen come from? Well, in the other steps, we had to add a hydrogen source in the second part, right? We said we allow this first part of the reaction to go forward, and then we add on some type of H+, so that way the oxygen can get the proton. Here we do not have to do that. Do you know why? Well, look at it. Look at the structure. That NH2 is a positive, and I told you that for now that nitrogen's okay with it. However, we're going to form a fully blown O- here. That O- is going to look for a proton, and if we do not give it a proton, it's going to look at itself and say, wait a minute, nitrogen, look, you're positive, and I'm negative. I would really like to have that proton that you carried with you to this party. And that nitrogen is going to say, okay, that's not a problem. So what I'll do is that I'll get rid of one of those hydrogens, so that way I do not need this positive charge anymore, and that is the hydrogen that goes there. So in other words, what I want you to think about is doing the hydrogen in front and then the CH3NH as the second part. The reason that I didn't do it like this in the beginning, though, is because you would have thought that this was an acid reaction because I separated hydrogen out from the pack, and it is not. NH2 is a base. It is an amine. Amines have very high pKa values, which mean very strong bases. One of the best nucleophiles that are out there on the market. Okay? So when you look at these, you have to understand that this is a base form that takes place, but this is also the hydrogen donor for the oxygen to form the alcohol up here. So we separate one of the hydrogens off. That's where that hydrogen is coming from. We're just not making it up. That's where it's coming from. It's coming from the nitrogen that gets added on. And again, that is why I do not need to add on a second step an H+ here. It already has it. It brought it to the party, and it's now ready to share it. All right, let's look at another one. Here, let's do a ring. We've not done one with a ring, really, right? So here is an epoxide on a ring, and let's bring in O- CH3, and we want to know what would happen. All right, so here's an epoxide. This is negative, so therefore this is a base. And then I look at this no, this is not an unsymmetrical. This one's the easy one, right? This is a symmetrical epoxide. I don't even have to think about it anymore, folks. So what I'll do is I'll just draw the ring, and I know that that ring's going to open up and 2 sides of attachment, one to the O and one to the other group is going to be there. So OCH3 will go onto one carbon, and then hydrogen will go onto that oxygen, so that way that forms an OH. What that also means is that in round 2, I'm going to have to add on some type of proton source for that to take place. Okay, so there is a wrap of base reactions with epoxides. So we've done acid reactions of epoxides, we've now done base reactions of epoxides, and now what I would like for you to do is to go back and try these on your own. So here's 4 more examples. For part A and part B, notice that these are unsymmetrical. To the left carbon, there's nothing attached, and to the right-handed carbon, we have 2 methyl groups attached. Okay? So these are unsymmetrical. It's very important that you think about how this oxygen is going to cleave. And then for parts C and D, the carbon to the left and the carbon to the right, those are identical. So that's a symmetrical epoxide. Again, symmetrical ones are always easier. So there's 2 methyls to the left, 2 methyls to the right. That epoxide's still going to open up. And if you notice, part A is in acid condition, part B is in base condition. And then for C, it goes back to acid, and for D, it goes back to base. So what they have done here to you is that on the left, unsymmetrical, one with acid, one with base. And then over here on the right-hand side, these are symmetrical ones, one with acid, one with base. So see if you can take a stab and draw a product and see what you come up with. And in the next video, we'll pick up from these 4 examples, and we'll draw out these reactions, and we'll predict the products, and we'll double check your answers against mine to see how well that you did.